Think of a complete nothingness. No darkness, no empty space, no time itself. Then ponder what might bring something, anything, into being from this nothingness. This is the greatest detective story ever told, and we are the mystery itself. 13.8 billion years ago, every molecule around you, every atom in your body, every star twinkling in the night sky, every space itself came into being in a burst so violent and instantaneous that the mind strains to comprehend it. It was the Big Bang, but even this term begins to scratch the surface of what really went on. The mystery of the beginnings of the universe isn't just about satisfying our curiosity. It's about understanding the very essence of our reality, the very rules by which everything functions, and our place in the universe itself. Are we random, or are we inevitable? Was something before the beginning itself, or are we beyond grasping? Keep watching till the end. For as long as humans have gazed up into the night sky, we have asked ourselves this same question. Where did it all come from? Every civilization, every society, and every culture has wrestled with this question. The Egyptians thought it came from primordial waters. The Norsemen spoke of a place called Ginnungagap, a great void. The Hindu scriptures described cycles of creation and destruction that spanned billions of years. They were myths, but they were also humanity's first attempts to grasp the meaning of existence. But then, something miraculous happened. In the 20th century, for the first time in human history, we were able to look beyond mythology and philosophy. We were able to look beyond mere speculation. We were finally able to grasp and understand the meaning of existence. What did we find? We found that it's stranger and more wonderful than any mythology or philosophy. It began in the 1920s when scientists first noticed that galaxies were moving away from us. And not only were they moving away from us, but the ones that were further away were moving faster than the ones closer to home. And that led to a revolution that would completely turn our understanding of existence upside down. Einstein's work, Hubble's observations, and breakthroughs in physics came together to create a new understanding of a universe that is not eternal and unchanging, but rather changing and beginning. And today, we'll take you through that revolution step by step. We'll start with an explanation of the Big Bang Theory, what it really is, and what evidence we have for it. And then we'll delve into some of the deeper waters and look at what happened before the Big Bang. And then, finally, we'll look at why it matters to us. So, let's rewind it back to the beginning. So let's clarify the biggest misconception about the Big Bang right off the bat. It wasn't an explosion in space, it was an explosion of space. The whole universe, all of space, condensed down to a single point that's smaller than an atomic nucleus and then suddenly expands in all directions at once. The key thing to realize about the Big Bang is that when we say the universe expands, what we don't mean is that all the galaxies in the universe are flying off in all directions like shrapnel from a bomb. What we do mean is that space itself is stretching out and all the galaxies in the universe are being carried along with it. Think of points drawn on the surface of a balloon. If you blow up the balloon, those points will move further and further apart, not because they're moving back and forth on the balloon's surface, but because the balloon's inflating out between them. So let's take a look at what exactly happened in those first moments of the Big Bang, which is almost incomprehensible. 10 to the negative 43 seconds after the Big Bang, 10 zeros, then a 1, the universe was hotter and denser than you can even begin to imagine. This moment in time is called the Planck time, and it's the earliest moment in the history of the universe that our current physics can even begin to describe. Before that, our equations don't apply at all. Within the first fraction of a second, the universe went through a process of exponential growth called cosmic inflation. In this process, the universe grew from subatomic size to perhaps the size of a grapefruit almost instantly. The temperature of the universe during this period was trillions of degrees and was so hot that not even atoms existed. Instead, there was a seething soup of particles and energy. After 1 second, the temperature of the universe dropped to 10 billion degrees. At this temperature, it was still much hotter than the center of our Sun. Protons and neutrons began to develop. At this time, the temperature dropped to a level where these particles began to combine to create the first atomic nuclei. Most of these nuclei were hydrogen and some helium and a small amount of lithium. However, it was still much too hot to create whole atoms. The universe remained an opaque fog of plasma for 380,000 years. Then, finally, it cooled enough for electrons to combine with nuclei, forming the first complete atoms. At this moment, light could finally travel freely through space. The universe became transparent, and the afterglow of that moment is something we can still detect today. But just how do we know that any of this really happened? After all, it's not like we can turn back time and watch it. Well, it seems that the universe has provided us with some evidence, and it is compelling. The most compelling evidence of all came by accident in 1964. Two radio astronomers, Arno Panzias and Robert Wilson, were trying to get rid of annoying static from their antenna. No matter what they did, however, they could not get rid of a hiss that seemed to be coming from every direction. What they had inadvertently done was to detect the cosmic microwave background radiation, or the afterglow of the Big Bang. Remember that moment 380,000 years after the Big Bang, when the universe became transparent? Well, that light has been traveling through space ever since. Today, that light is microwave radiation, and it is 2.7 degrees above absolute zero. It is a faint glow that permeates every corner of the universe. Penzias and Wilson won the Nobel Prize for their discovery, and it has since been extensively explored, showing minute fluctuations that would eventually form galaxies. The second big piece of evidence comes from what we see when we look at distant galaxies. In the 1920s, a man named Edwin Hubble made a tremendous discovery. When he looked at distant galaxies, he found that the light coming from them was shifted towards the red end of the light spectrum. When things move away from us, their light is shifted towards the red end. This is called redshift. The more distant a galaxy is, the faster it's moving away from us. This is called Hubble's law, and it's exactly what we'd expect if space is expanding. If everything is moving away from each other now, that means that everything used to be closer together at some point. If we go far enough back, everything comes together at one point. That's the Big Bang. The third pillar of evidence is the amount of light elements that exist within our universe. The Big Bang theory predicts specific amounts of hydrogen, helium, and lithium that were created within the first few minutes after the Big Bang. When scientists measure these amounts, they are found to be precisely what the theory predicted. The universe is composed of 75% hydrogen, 25% helium, and trace amounts of other light elements, precisely as predicted by the Big Bang theory. These three pillars of evidence do not merely indicate that the Big Bang theory actually took place. Rather, they fit so neatly together that it is nearly impossible to dispute the fact that this theory is correct. We are not talking about speculation. Rather, this is one of the most tested theories within science. Let's review what actually took place in those first few minutes with the confidence that comes from hard evidence and theory. The first 3 minutes after the Big Bang were a time unlike any other. The universe began as pure energy at unimaginable temperatures, with particles and antiparticles being created and destroyed. As the universe expanded and cooled, quarks began coming together to form protons and neutrons. These nuclear particles then came together in a process called Big Bang nucleosynthesis. This was no ordinary star formation, but rather a universal one. In a few minutes, a quarter of all ordinary matter in the universe was changed into helium nuclei. The great majority of the remainder was single protons, or hydrogen nuclei. This mixture has remained remarkably constant throughout the entire history of our universe. For 380,000 years, the universe was still much too hot for atoms to form. The electrons were unable to settle down into stable orbits around the atomic nuclei, since photons were continually knocking them loose. The universe was opaque, a blinding fog that light could travel only a short distance before being absorbed and then re-emitted. Then came the moment of recombination. As temperatures cooled to below 3,000 degrees, electrons at last began to combine with nuclei to form stable atoms. Suddenly, photons were free to travel. The universe became transparent, and this is the moment whose afterglow we see in the cosmic microwave background. But the universe remained dark. No stars existed, only clouds of hydrogen and helium floated through space. This period, called the Cosmic Dark Ages, lasted 100 million years. Then, matter began to clump together under gravity's pull. The first stars flared to life, brilliant and massive, burning fuel at a furious rate and exploding as supernovas. In the process, they scattered heavy elements like carbon, oxygen, and iron into space, elements unknown before. Billions of years went by as this process continued. Galaxies formed, stars were born and died in cycles, and the universe evolved into the magnificent creation we see today. A cosmic web of galaxies, clusters, and vast voids stretching out into space, all moving away from each other in the grand dance that began 13.8 billion years ago. Now, on to the really mind-bending stuff. What was before the Big Bang? It's a perfectly natural question, but it may actually be a meaningless one, and that's what I'll explain next. Time, it seems, actually began with the Big Bang. And this is no theory, but rather a direct result of Einstein's theory of general relativity. As mentioned earlier, space and time aren't separate things. Rather, space and time are joined together in a four-dimensional fabric called space-time. If space began expanding at the Big Bang, then time began at that same event. To illustrate this, think about this. What's before the Big Bang is rather like asking what's north of the North Pole. The implicit assumption that makes this question sensible doesn't actually hold up. Before is a time-related term, implying earlier times. But since time began at the Big Bang, there actually was no before. The Big Bang wasn't something that took place within time. Rather, it was the beginning of time itself. And that leads us nicely into the singularity problem. If we follow our equations backwards towards the beginning of time, then we eventually reach a singularity, where our equations produce infinities and space has infinite curvature. In other words, physics, as we know it, ceases to function. The temperature becomes infinite, space becomes infinitely curved, and our equations produce nonsensical infinities. The singularity, most physicists think, doesn't actually exist, but rather indicates that our equations, general relativity, aren't quite correct. It's telling us that what's needed is a theory that combines general relativity and quantum theory, a theory of quantum gravity. We don't have that theory, at least not yet. Despite these challenges, physicists have put forward some intriguing ideas about what might have led to the Big Bang. Let's take a look at some of the most intriguing ideas. First off, there is the cosmic inflation theory. While this theory doesn't quite answer what led to the Big Bang, it answers some of the biggest questions about what followed. According to this theory, which was first put forward by Alan Guth and others in the 1980s, the universe grew exponentially in the first fraction of a second of its life. In fact, it grew by a factor of at least 10 to the 26th power almost instantly. This growth is attributed to a special field, like the Higgs field, which is responsible for the anti-gravity effect. This theory explains why the universe is so homogeneous. In other words, all directions of the universe look more or less the same. In fact, regions of the universe that appear to be out of reach of each other were actually in contact before the Big Bang. Inflation theory also explains the formation of matter within the universe. Quantum fluctuations, which occurred during the inflation period, eventually became the matter that formed the galaxies. The quantum fluctuation pattern is a perfect fit for what is actually observed. There is also the quantum fluctuation theory. This theory addresses the biggest question of all: what can be created from nothing? Quantum mechanics has shown us that nothing is actually quite busy. In a perfect vacuum, particles and antiparticles appear and disappear all the time. Other theories, such as that proposed by Lawrence Krauss, go so far as to posit that perhaps our own universe is actually a manifestation of a quantum fluctuation. In a quantum world, anything that is not forbidden is allowed to happen with enough time, so with an eternity of nothing, anything can happen. The entire universe, with all its energy, could be a quantum fluctuation from a quantum vacuum. The energy in matter and radiation could be balanced by negative gravitational energy, so that the net energy is zero. A free lunch from the quantum cookbook. Multiverse theories propose a different explanation. What if our own Big Bang was not unique in the first place? In eternal inflation theories, inflation never actually stops. Inflation stops in some areas, creating our own universe bubble, but in others it continues, creating an infinite number of universes with different physical laws and constants in each one. Our own universe is simply one bubble in an endless sea of cosmic bubbles. String theory proposes yet another multiverse theory, called the landscape of string theory, with perhaps 10 to the 500th power different universes, with different configurations of forces and particles. We simply happen to live in one that allows for life, but not because it is in any way special, simply because we could not exist in a universe with different parameters. The cyclic theories recall ancient Hindu mythology, in which the universe cycles endlessly. In cyclic theories, our own Big Bang was simply not a beginning, but simply an event in an endless cycle. Each cycle takes trillions of years: a Big Bang, a time of expansion, a time of contraction, a big crunch, and then another Big Bang. Time is endless, with no beginning or end. We have arrived at the frontier of human knowledge, where known science gives way to educated speculation and ongoing research. The search for answers about cosmic origins has taken physicists into some of the most abstract and mathematical realms ever conceived. Quantum cosmology and quantum field theory have given us some of the most important insights yet into the workings of the universe. Quantum field theory assures us that what appears to be empty space is actually teeming with activity, as fields permeate all of space and particles are simply an excitation of these fields. If you extend this theory back into the early universe, what you get is a reality fundamentally at odds with what we experience. At the Planck scale, distances of 10 to the negative 35 meters and times of 10 to the negative 43 seconds, space and time may become grainy and probabilistic. According to some theories, space-time is actually made up of yet more fundamental elements, such as quantum loops. To ask at what time and where something occurred may be as meaningless as asking the precise position and momentum of a quantum object. One of the most promising approaches toward creating a theory of quantum gravity is string theory, which postulates that the fundamental building blocks of reality are not point-like particles, but tiny vibrating strings. These strings exist in 10 dimensions, with one dimension being time and the other 9 being spatial dimensions. The additional dimensions are curled up so tightly that they are not accessible at everyday energy scales. Different vibrations of these strings give rise to different particles. An electron and a quark have different vibrations. According to string theory, the Big Bang might have been an event in which all dimensions of space expanded rapidly, while others remained microscopic. Some versions of string theory propose that our universe is simply one brain or membrane in a higher dimensional space, and that matter and energy were created when two brains collided. And then there's dark energy and dark matter, which add another layer to this cosmic enigma. We currently know that ordinary matter, which makes up atoms, stars, and galaxies, makes up only 5% of our universe. Another 27% is dark matter, which is invisible but whose gravity is used to govern galaxies. The remaining 68% is dark energy, which is driving the acceleration of the universe's growth. In order to solve the enigma of where the universe came from, we also need to solve the enigma of where dark matter and dark energy came from. Were they present from the start, or did they emerge at some point? Does dark energy have something to do with vacuum energy, which is present in empty space, and which could be responsible for cosmic inflation? Despite all these advances, some questions remain unanswered, and some may remain beyond the reach of our current knowledge. The biggest enigma is surprisingly simple. Why is there something rather than nothing? Why do quantum fields exist? Why do physical laws exist? Some philosophers and physicists argue that this is a question beyond science, a question of metaphysics. Others believe that perhaps one day we will be able to develop a theory that makes existence more natural than nothingness, but we're not there yet. The question of fine-tuning is just as baffling. The basic constants of nature, the strength of gravity, the mass of the electron, the cosmological constant, are all precisely calibrated to allow the existence of complex structures like stars, planets, and life. Tweak any of these constants slightly, and the universe might be a lifeless place. Stars might never have been born, atoms might be unstable, or the universe might collapse just after the Big Bang. Is this mere coincidence, evidence of design, or are we living in a multiverse where physical constants vary, and we just happen to live in a universe that allows for our existence? The anthropic principle does not answer the question. It merely puts it into perspective. We cannot observe a universe that is not compatible with our existence. The mystery of matter and antimatter is also not fully explained. Matter and antimatter were produced equally in the early universe. When matter and antimatter combine, they annihilate and turn into photons. So why did matter and antimatter not annihilate completely, leaving a universe composed of photons and nothing else? There had to have been a slight excess of matter, an extra matter particle for every billion matter/antimatter pairs. This is why we have matter and anything exists today, but why it is so is unknown. Physicists are coming at these problems from many different angles. Particle accelerators are searching for evidence of new physics beyond the standard model. Gravitational wave detectors might detect evidence from the earliest moments of the universe. New and improved telescopes are studying the cosmic microwave background radiation, searching for evidence that can confirm or refute different inflation models. You might wonder, why bother going to these extremes to find the beginning of everything? It sounds like a rather abstract and remote endeavor, and not really relevant to everyday life. But the search for the beginning of the universe has, in fact, been beneficial and has given us some tremendous insights into the universe and the world around us. The technology spin-offs have been a big help to other fields as well. For instance, the sensors developed to detect the cosmic background radiation have been beneficial for medical imaging. The computer algorithms developed to analyze the universe's starlight have been beneficial for other computer applications like medical scans and weather forecasting. The GPS technology in your car relies on the relativistic corrections derived from Einstein's theories, the same theories we use to understand the Big Bang. The particle physics experiments to simulate the conditions in the universe have also been beneficial. The World Wide Web was first developed at CERN to help physicists communicate and collaborate. PET scans in hospitals use antimatter, a prediction derived from the equations of particle physics. The technology to detect particles has been beneficial for quantum computing, a technology that promises to revolutionize information technology. But the benefits of understanding the beginning of the universe are not limited to technology. It has philosophical and cultural implications as well. Understanding the beginning of the universe has made us realize that we are not separate from the universe, we are a part of the universe. Every atom in your body was created in the heart of a dying star. You are, in effect, made of stardust, and there is a chain of cause and effect between you and the Big Bang. This approach carries with it a measure of humility and wonder. We are small in a universe that is beyond comprehension in its size and age, yet with human consciousness, the universe is conscious of itself, which is a wondrous thing. Understanding our cosmic origins also provides context for humanity's challenges. Climate change, geopolitical conflicts, economic inequalities, these seem enormous from our limited perspective. But viewing Earth from the cosmic scale reminds us that we share a fragile planet, the only known harbor of life in a vast and indifferent universe. This perspective doesn't diminish our problems, but frames them differently, encouraging cooperation and long-term thinking. The drive to understand cosmic origins reflects something essential about human nature. We're curious, pattern-seeking beings who yearn to understand our place in the grand scheme. This pursuit stretches our minds, challenges our assumptions, and pushes the boundaries of what's knowable. In studying the universe's beginning, we're engaging with the most fundamental questions existence poses. The Big Bang Theory is one of the greatest achievements in science, supported by several lines of independent evidence: the cosmic microwave background, the redshift of distant galaxies, and the amounts of light elements produced in the Big Bang. We are confident that the Big Bang marked the beginning of the expansion of the universe 13.8 billion years ago, from an extremely hot and dense state. We understand the broad strokes of the Big Bang, how particles were created, how atoms were formed, and how gravity shaped the large structures we see in the universe today. However, there are many things that remain a mystery to us. We do not know what, if anything, existed before the Big Bang, or whether it is even meaningful to ask this question. We do not yet have a complete theory of everything that merges quantum mechanics and gravity, which is required to understand the Big Bang itself. We do not yet fully understand why there is something rather than nothing, why the universe is finely tuned for life, or how dark energy and dark matter fit into the Big Bang picture. Thanks for watching, and keep looking up.